Another solubility calculation examples. The solubility of ionic product M2X3 and the molar mass is given 288 gram per mole is 3.6 times 10 minus 17 gram per liter. What is KSP? First of all, in this example, the solubility is given in gram per liter, so this is the mass concentration. And when we talk about KSP, we talk about ionic product of concentration. So we have to transform the mass concentration to the molar concentration. What are the steps in this exercise? First of all, you have to write correctly the dissociation M2X3 solid that will dissociate partially. For example, 2M, suppose 2M 3 plus 3x 2 minus. Suppose that the ions is given by this way. So you put directly 2s and here you put 3s. This is step 1. Step 2, you write the expression of KSP. KSP is equal to the concentration of M3 plus at equilibrium to the power 2, since we have stoichiometric coefficient 2 times the concentration of x2 minus at equilibrium to the power 3. This is the second step 2. Equal M3 plus at equilibrium is 2s square times 3s to the power 3. And pay attention that this solubility should be in mole per liter. But the solubility given in the exercise is a gram per liter. So this is in mole per liter. We have to transform the solubility gram per liter, okay, to mole per liter. Cm equal the mass concentration, the molar concentration is equal to number of moles of the solute divided by the volume of the solution, equal the number of mole of the solute equal mass divided by molar mass divided by the volume of the solution. The mass over volume is the mass concentration divided by the molar mass. So to transform the solubility from gram per liter to mole per liter, we have to do the ratio S equal the mass concentration is 3.6 times 10 minus 17 divided by the molar mass, which is given 288. So we calculated the solubility is equal 1.25 times 10 minus 19 mole per liter. Then we put S by its value in the expression of KSP, and therefore we calculated KSP. Okay, so pay attention for the written of the KSP according to the solubility or according to the concentrations in mole per liter. Comparing the solubilities of two different salts. Suppose you have two beakers containing the same volume of water and you add the same amount of BaSO4 and PbI2. So in beaker 1, you add BaSO4. In beaker 2, you add PbI2. And the question is, which of the two solids is more soluble? First of all, BaSO4 is characterized by KSP and PbI2 is characterized by K'Sp. Since KSP or K are given, that means BaSO4 is weak electrolyte and PbI2 is weak electrolyte. So this is the first indication from the KSP value. Both are weak electrolytes. The second question, what would happen in beaker 1 and what would happen in beaker 2? In beaker 1, BaSO4 will dissociate partially to ions Ba2 plus and SO4 2 minus. So BaSO4 is partially soluble. In beaker 2, PbI2 dissociate partially to Bb2 plus and I minus. So PbI2 is also partially soluble. So the question now, which is more soluble? Which is more soluble? In other question, or in other word, which would give a higher concentration of ions? So the question now, should we do calculations or according to the KSP value, we can know directly which is more soluble? In chapter 1, we studied in the introduction, chapter 0, we studied in the introduction, when we have two reactions possible, we can study the sequence of these two reactions by comparing K of the reactions. What is K of reaction 1? K of reaction 1 is K1 equal KSP. K of reaction 2 is K2 equal K prime SP. To know which is more advanced, that means which will give more concentrations or more amount of ions, we can compare K of the reactions at condition that the two reactions have the same stoichiometry. In reaction 1, the stoichiometry is 1, 1, 1. In reaction 2, the stoichiometry is 1, 1, 2. Since these two reactions or these two dissociations do not have the same stoichiometry, so the value of K of the reaction could not be compared. That means KSP and K prime SP could not be compared. The error in concept by the student will say the solid that has greater KSP, that means the dissociation is stronger, that means is more soluble. Yes, you can use this concept if you can compare these two dissociations. So you can use this concept if the dissociation of the two weak electrolytes follow the same stoichiometry. In this case, we have two dissociations of different stoichiometries, so the value of KSP could not be compared. AGI, KSP equal 1.5 10 minus 16, CUI equal KSP 5 10 minus 12, CaSO4 equal KSP 6.1 10 minus 5. If we look to the stoichiometries of this solid, this is 1, 1, this is 1, 1, and CaSO4 is also 1,1. In this case, we can compare their dissociations according to the value of Ksp. The higher Ksp, the greater Ksp means the greatest or the highest solubility. If we compare AgI, CuI, CaSO4 without doing calculations in order to know the solubility, you can compare directly their values of Ksp since the stoichiometry of the solids is the same, which has higher Ksp. This is Ksp 10 minus 5, 10 minus 12, 10 minus 16. So CaSO4 is more soluble in solution than CuI, more soluble than AgI. So keep in mind that the value of Ksp is an indication about the solubility if the solids you compare have the same stoichiometry. Example, compare the solubilities of the following weak electrolytes of the saturated solutions of the weak electrolytes CuS, Ag2S, Bi2S3. Ksp of CuS, Ag2S, and Bi2S3 are given. Okay? Since the stoichiometry of these weak electrolytes are different, this is stoichiometry 1,1, this is stoichiometry 2,1, this is stoichiometry 2,3, so you could not compare the values of Ksp. So what to do to more which has highest solubility is to calculate the solubility in each case. CuS will give S and S. So Ksp equal S square. So S equal radical Ksp equal 9.92 10 minus 23. Ag2S Ksp equal, here we have 2S, 1S, so Ksp equal 2S square times S to the power 1, so equal 4S3. So the solubility S or X, don't forget that X can be written as, is equal radical 3 Ksp divided by 4 equals 6.4 10 minus 21. And in case of Bi2S3, the X is equal radical 5 Ksp divided by 4 times 27. Okay. Why? Since Ksp equal 2S to the power 2 times 3S to the power 3. So equal 4S2 times 3 to the power 3 times S3. So you have the ratio 27. So equal 1.003 times 10 minus 15. So which is more soluble? 10 minus 23, 10 minus 25, 10 minus 15. So Bi2S3 has a greater solubility. Solubility and common ion. We explained in the acid base what is the meaning of the common ion. When you have Ha that is put in water, Ha will dissociate to A minus and HCO plus. You can dissolve Ha in a solution containing initially A minus, or you can dissolve Ha in a solution containing initially H2O plus. A minus that is present initially in the solution is common ion with the A minus of Ha. HCO plus that is present initially in the solution is common ion with Ha. So this is the definition of the common ion. What is the objective of this part? The objective of this part, you have two beakers. In the first, you have a pure water. In the second, in the first, you have pure water, only H2O. In the second, you have solution H2O containing initially N plus and Cl minus. So the question, what is the solubility in case of pure water? And what is the solubility in case of NaCl solution? So should we do calculations, or we can have conclusion directly from the beginning? First, NaCl will dissociate the AgCl will dissociate partially to Ag plus and Cl minus. And in the second, AgCl will dissociate partially to Ag plus and Cl minus. According to Le Chatelier principle, if the concentration of Ag plus increase, the equilibrium will shift in direction backward. Or at equilibrium, if you add Cl minus, the equilibrium will shift backward. So in this solution, suppose you have AgCl that will dissociate to Ag plus and Cl minus. In the second, the AgCl is dissolved in a solution containing Ag plus and the Cl minus. So in case of AgCl in NaCl solution, the equilibrium will shift backward. Why? Since Cl minus is provided initially by the solution of NaCl. What is the meaning of equilibrium that will shift in direction backward? That means the solubility of AgCl, which is in this case S prime, the solubility of AgCl, S of AgCl, and here we have solubility of AgCl. The solubility of AgCl in case you have common ion Cl minus is less than the solubility in case you have a pure water, since the equilibrium will shift backward. So S is less than the initial solubility. In other words, NaCl dissolve in a pure water AgCl dissolve in a pure water greater than AgCl in a solution containing initially the common ion Ag plus or Cl minus. So the solubility of AgCl in a solution containing the common ion is less than the solubility of AgCl in case of pure water. You can conclude directly that the solubility in case of the common ion will decrease. So the solubility of AgCl in a solution containing 0.02 NaCl solution, Cl minus is the common ion between AgCl and NaCl. So in this case, you will decrease the solubility. I will go to the calculations and I will prove that the solubility in pure water is greater than the solubility in a solution containing the common ion. In pure water, AgCl dissociate to Ag plus and Cl minus. So at equilibrium, we have S and S. Since at T equals 0, 0, 0, At T equilibrium, we have formation X at X. In case of AgCl, in NaCl solution at T equals 0, we have Ag plus equals 0, practically 0, but Cl minus is not equal to 0 since the solution contains initially Cl minus ion, which is equal in the exercise, which is equal 0.02. So the dissociation will proceed till the equilibrium. At equilibrium, we have 0 plus X, so S, and we have 0.02 plus X or 0.02 plus S. KSP of AgCl in both cases is the same, since KSP is an equilibrium constant that depends on the nature of the solute, which is AgCl in both cases, and also it depends only on the temperature. In equilibrium 1, the temperature is 25 degrees. In equilibrium 2, the temperature is 25. So KSP is the same in both equilibriums. KSP equal Ag plus times Cl minus equal SS times equal S square. In case 2, KSP equal Ag plus at equilibrium, Cl minus at equilibrium equal S times 0.02 plus S. And pay attention, S in case 2 is not the S in case 1. This is notation only S. Okay? So we have to solve this quadratic equation to obtain S. And in case 1, S is equal radical KSP. Since we know that in case 2, the solubility will be very low due to the presence of the common ion, we can say, if we don't want to calculate the quadratic equation, is to neglect S with respect to 0.02. So KSP equal S times 0.02. So S is equal KSP divided by 0.02. If you compare these values, you will obtain the solubility in case of pure water is greater than the solubility in case of a solution containing initially the common ion. So as a conclusion, the common ion will decrease the solubility of a weak electrolyte. So you can use it directly without calculation. Or in other words, the solubility of a weak electrolyte in a pure water is greater than the solubility of the same weak electrolyte in a solution containing initially the common ion. What are the factors that affect the solubility? Consider AgCl in water that will dissociate partially till the equilibrium to Ag plus and Cl minus. If we shift the equilibrium in direction 1, so we increase the solubility. If we shift the equilibrium in direction 2, we decrease the solubility or we increase the precipitation. The term decrease solubility means increase precipitation, since the solubility is the inverse of the precipitation. So the question now, what are the ways to increase the solubility of AgCl? In other words, what are the factors in order to shift the equilibrium in direction 1? Increasing solubility means shift the equilibrium in direction 1. To shift the equilibrium in direction 1, we have two ways. One is to decrease Ag plus at equilibrium. Two is to decrease Cl minus at equilibrium. The question now, can the pH of the solution affect the shift of the equilibrium? If Ag plus interact with water, or if Cl minus interact with water, that means the equilibrium can be shifted in direction 1 or direction 2. But you know that Ag plus is a spectator since it does not appear in a couple acid base, and Cl minus is a spectator ion since it does not appear in a couple HAA minus. In other words, the change of the pH of the solution in case of AgCl has no effect since H3O plus or the pH does not affect Ag plus nor Cl minus. Ag plus and Cl minus are spectator ions. So the question now, can the pH of the solution affect the solubility of AgCl? No. So what is the other ways in order to increase the solubility? Consider the example CaC2O4 solid given Ca2 CaC2O4 solid has a KSP, and in the exercise given H2C2O4 HC2O4 minus, which has Ka1, and HC2O4 minus C2O4 2 minus has a value Ka2. KSP, Ka1, and Ka2 are given. The question now, does the pH of the solution affect the solubility of CaC2O4? First of all, I will ask the question, what would happen when CaC2O4 is put in solution? First, CaC2O4 is a weak electrolyte since we have a value of KSP. And the weak electrolyte dissociates partially to ions till the equilibrium, and at equilibrium we have KSP equal the concentration of Ca2 plus at equilibrium times C2O4 2 minus at equilibrium. The second question, can we shift the equilibrium in direction 1 or in direction 2 in order to modify the solubility? The question now is to study the nature of the ions formed. Ca2 plus is a spectator since it does not appear in a couple acid base. We don't have any given couple acid base containing Ca2 plus. So Ca2 plus is a spectator. C2O4 2 minus is a weak base since it appears in the couple HC2O4 minus C2O4 2 minus. What is the meaning of this statement? C2O4 2 minus is a weak base. That means if you add HCO plus, it will react with C2O4 2 minus. So C2O4 2 minus will decrease. C2O4 2 minus will decrease. And in this case, CaC2O4 will shift in direction 1. So the pH has a strong effect on the dissociation of CaC2O4. Suppose you don't add HCO plus or OH minus at equilibrium. Since C2O4 2 minus is a weak base, that means it will interact with water. And when C2O4 2 minus interact with water, it will give HC2O4 minus plus OH minus, and HC2O4 minus will react also with water to give H2C2O4 plus OH minus. The equilibrium constant, or K of the reaction, 1 is equal to Kb1, and K of reaction 2 is equal to Kb2. And Kb1, Kb2 can be deduced from Ka1 and Ka2. So in this case, since one of the ions formed appears in a couple acid base, in other words, one of the ions formed interact with water, in this case, the pH will affect the solubility of the weak electrolyte given. In the previous example, we have AgCl that dissociate to Ag plus and Cl minus. Ag plus is a spectator ion, does not interact with water. Cl minus is a spectator ion, does not interact with water. So the dissolution of AgCl is not affected by the pH of the solution. In the case of CaC2O4, one of the ions, which is C2O4 minus, appear in a couple acid base, so it will interact with water, or it will interact, suppose you add HCO plus or you add OH minus. So in this case, the pH has effect on the solubility. And the question now, for example, what should be the pH of the solution in order to dissolve 10%? What should be the pH of the solution in order to dissolve 50%? Or what is the pH of the solution in order to dissociate completely the CaC2O4? One of the daily example, an example of our daily life, is the calorimeter or the heater of water. You have water that is heated, and after, for example, few months, you observe that you have formation of solid on the resistance. So what to do? You have to increase the solubility. You have to dissolve this weak electrolyte that is formed. You add, for example, acid in order to dissolve it. What is the meaning you add acid? That means this weak electrolyte has ion that is affected by the acid added. So, as a conclusion, the pH will affect the solubility of a weak electrolyte if one ion or the two ions obtained from this weak electrolyte interact with water or appears in a couple acid base. I will pass directly to an example. Consider CaC2O4 with KSP given. What would happen when you add HCO+? Pay attention for the sequence of the solution. Without addition or before addition of CaC2O4. Before addition of HCO+, I have water, so I add CaC2O4. What would happen? This is case 1. 1, CaC2O4 is a weak electrolyte. Since we have a value of KSP given, it will dissociate to ions partially till the equilibrium Ca2 plus, C2O4 minus. The second question now, you have HCO plus that will be added to the beaker. So the question, what would happen when adding HCO plus, or what would happen when the pH of the solution decreases? What are the ions present initially in the beaker? In the beaker, we have Ca2 plus and we have C2O4 minus at equilibrium. Ca2 plus is a spectator ion since it does not appear in a couple acid base. So Ca2 plus does not make reaction with HCO plus. It does not interact. C2O4 minus is a base. Previously, we know that from the couples given, C2O4 minus is a base. It will react with HCO plus. So adding HCO plus means the concentration of C2O4 minus at equilibrium will decrease, implies, according to Chatelier, the equilibrium will shift in the direction 1. The equilibrium will shift in direction 1. What is the meaning the equilibrium will shift in direction 1? That means adding HCO plus C2O4 minus react, decrease, the equilibrium will shift in direction 1 implies the solubility will increase. This is qualitative. The solubility will increase. So if you have multiple choices, the solubility remains the same, the solubility decrease, the solubility increase, none of these answers, you can qualitatively know the answer, the solubility will increase. So C2O4 minus will react with HCO plus to give HC2O4 minus H2O, and also HC2O4 minus, which is a base in the second couple. We have two couples, H2, C2O4, HC2O4 minus, and HC2O4 minus, C2O4 minus. As you observe, HC2O4 minus will play the role of base or the acid. So we have another reaction. C2O4 minus will react to H plus to give H2C2O4 minus, and H2C2O4 minus will react with H plus to give H2C2O4. So we have three reactions. Three reactions are possible. What is the sequence of these three reactions? Should we calculate K of reaction 1, K of reaction 2, or K of reaction 3? Therefore, to compare K1 is greater 100 times than K2. First of all, reaction 1 could not be compared to reaction 2. Since the stoichiometry in reaction 1 is 1, 1, 1, 1, 1, 1, the stoichiometry in reaction 2 is 1, 1, 1, 1. So K of the reactions could not be compared in order to know the sequence. So what is the sequence of these three reactions? These three reactions occurs at the same time. Why? When C2O4 minus react with HCO plus, directly C2O4 minus in reaction 1 decrease. So when reaction 2 occurs, at the same time reaction 1 occurs. When HCO plus react with C2O4 minus, that means C2O4 minus will decrease. That means C2O4 minus in reaction 1 will decrease. That means reaction 1 will shift in direction 1. So the sequence of these reactions, now the three reactions occurs at the same time. And when we have several reactions possible at the same time, we could not work on reaction 1, nor in reaction 2, nor on reaction 3. We work on the global reaction. Keep in mind, in this type of the exercises where the pH affect the solubility, you have to work on the global reaction. The global is CaC2O4 plus 2HCO plus, C2O4 minus, C2O4 minus cancelled, give Ca2 plus, HC2O4 minus, HC2O4 minus cancelled. So we obtain Ca2 plus H2C2O4 plus 2H2. We have to calculate K global and we have to work on this reaction. This is the reaction we work on. Pay attention that now we have a new type of exercises. We have to work on the global reaction. What is the objective? Don't forget that the question is, what is the effect of HCO plus added? As to know the effect of HCO plus added, we know qualitatively that the solubility will increase. That means Ca2 plus will increase. So if we calculate the concentration of Ca2 plus at equilibrium in the global reaction, in other words, we know what is the effect of HCO plus added from the beginning. And do not forget that as you add HCO plus, you form more Ca2 plus. So Ca2 plus is directly related to the addition of HCO plus. So the question now, what is the concentration of Ca2 plus at equilibrium? When we work on the global reaction, to know the strategy of calculation, we have to calculate K global, and to know if the reaction is complete, we work at T equal infinity. And if the reaction is incomplete, we work at T equilibrium. So now we have to find what is K global. K global is equal Ca2 plus at equilibrium times H2C2O4 at equilibrium. H2 is not counted. Divided by Ca divided by HCO plus square. This is K global. This is the expression of K global. And given KSP, KA1, and KA2. No, given KSP, KSP is given, KA1, and KA2. So we have to calculate K global as a function of KSP, KA1, and KA2. What to do? K global equals Ca2 plus divided times H2C2O4 divided by HCO plus square. So I have to multiply. I will multiply by C2O4 to minus, C2O4 to minus, HC2O4 minus, HC2O4. Why I multiply by this concentrations? In order to appear KSP and to appear KA1 and KA2. Ca2 plus times C2O4 to minus is KSP. C2O4 to minus times HCO plus divided by H2C2O4 minus, this is Ka2. So C2O4 to minus times HCO plus divided by H2C2O4 minus, this is Ka2. H2 HC2O4 minus times HCO plus divided by HCO2 divided, excuse me, I have to write KSP equal Ca2 plus times C2O42 minus Ka1 equal HC2O4 minus times HCO plus divided by H2 C2O4 Ka2 equal C2O42 minus times HCO plus divided by HC2O4 minus. So K global, if you put KSP, Ka1 and Ka2 expression, you obtain K global equal KSP divided by Ka1 times Ka2. So we calculated K global. This is question 1. Now we have to know from the value of K global, the reaction is complete or incomplete. If the reaction is complete, so we have to calculate Ca2 plus at T equal infinity. If the reaction is incomplete, we calculate Ca2 plus at T equilibrium. So the value of K global is an indication. If K global is very high, the reaction is complete. If K global is very low, the reaction is incomplete. And in this case, in both cases, you can calculate Ca2 plus at the equilibrium state. If you calculate Ca2 plus at equilibrium, T equal infinity or T equilibrium, Ca2 plus is obtained from the addition of HCO plus, so you can know what is the effect of HCO plus. We will solve in details these types of questions. Now I explained only the strategy of solution. We will solve it in details.